Right now, in 2026, we still cannot explain how the universe actually works. And I'm not exaggerating. We have two incredible theories that describe reality. Quantum mechanics explains the tiny world of atoms. General relativity explains massive objects like stars and black holes. But here's the problem. These two theories completely contradict each other. They cannot both be true. Yet experiments prove both of them work perfectly in their own domains. The theory of everything is the holy grail that would finally unite these theories into one elegant equation. One formula to rule them all. By the end of this video, you'll understand why finding this theory is so maddeningly difficult and what it would mean if we actually solved it. To understand the theory of everything, we first need to talk about the four fundamental forces. Everything that happens in the universe is controlled by just four forces. Gravity keeps your feet on the ground and holds galaxies together. Electromagnetism powers every electronic device and creates light itself. The strong nuclear force glues atomic nuclei together. Without it, every atom would explode. The weak nuclear force causes radioactive decay and powers the sun. Here's the crazy part. Physicists successfully unified three of these forces in the 1970s. Electromagnetism and the two nuclear forces all spring from the same quantum field. This unified theory is called the Standard Model of particle physics. It has been tested in thousands of experiments. It predicted the Higgs boson decades before we found it in 2012. But gravity refuses to join the party. Every single attempt to merge gravity with quantum mechanics has failed spectacularly. Over 99% of the universe is perfectly explained by either quantum mechanics or general relativity, but not both at once. Einstein spent the last 30 years of his life obsessed with finding a unified theory. He covered thousands of pages with equations trying to merge gravity and electromagnetism. He failed, and he knew he failed. On his deathbed in 1955, he had pages of calculations next to him. Still searching, still trying. But Einstein was missing a crucial piece. He didn't fully accept quantum mechanics. He famously said God does not play dice with the universe. He was wrong about that. Modern physicists know any theory of everything must include quantum mechanics. You cannot ignore the quantum world. It's too fundamental to reality. So the real challenge became clear. We need a quantum theory of gravity. This is where things get absolutely wild. In the Standard Model, forces are carried by particles. Photons carry electromagnetism. Gluons carry the strong force. W and Z bosons carry the weak force. So physicists assumed gravity must have a particle too. They called it the graviton. But nobody has ever detected one. Not even close. When you try to calculate quantum gravity using normal methods, you get infinity. Not a big number. Literal mathematical infinity. The equations explode and become meaningless. This happens because gravity gets stronger and stronger at smaller scales. At distances smaller than the Planck length, space-time itself becomes a foaming quantum mess. The Planck length is unimaginably tiny, about 10 to the negative 35 meters. That's a decimal point followed by 34 zeros and then a 1. At this scale, our current physics completely breaks down. We have no idea what happens, and we cannot build experiments to test it. The energies required are impossibly high. To probe the Planck scale directly, you would need a particle accelerator the size of the entire galaxy. We're not building that anytime soon. This is why quantum gravity is so brutally hard. We need a theory that works at scales we can never directly observe with current technology. So physicists got creative. They invented entirely new mathematics to solve the problem. Enter string theory. In the 1980s and 90s, this became the hottest idea in physics. Thousands of the smartest people alive worked on it. String theory says particles are not points. They're tiny vibrating strings of energy. Different vibrations create different particles. An electron is one vibration pattern. A quark is another. The math of string theory naturally includes gravity. The graviton emerges automatically from the equations. This was huge. It seemed like we finally had quantum gravity solved. There was just one tiny problem. String theory requires 10 dimensions of space, not 3. 10. Where are the other 7 dimensions hiding? The answer is they're curled up incredibly small, so small we cannot detect them. Every point in space contains 6 extra dimensions rolled into complex shapes called Calabi-Yau manifolds. But then came an even bigger problem. There are about 10 to the 500 different ways to curl up these extra dimensions. That's more possible universes than atoms in our universe. This is called the landscape problem. String theory does not predict one universe. It predicts 10 to the 500 possible universes. How do we know which one is ours? Worse, string theory has made 0 testable predictions in over 40 years. Not one. We cannot prove it right or wrong with any experiment we can actually do. By 2026, many physicists have given up on string theory. Some call it a beautiful mathematical fantasy that has nothing to do with reality. So what else do we have? Loop quantum gravity is the main alternative. It says space-time itself is made of tiny discrete loops woven together like fabric. Loop quantum gravity avoids the infinity problems and does not require extra dimensions, but it struggles to include the other forces. It only handles gravity well. Some physicists think we are asking the wrong question entirely. Maybe there is no theory of everything. Maybe the universe is fundamentally incomprehensible to human minds. Others believe we are missing a crucial insight, some radical new idea that will make everything click, like when Einstein realized space-time could curve. Here's what we do know. The theory of everything must explain dark matter and dark energy. These make up 95% of the universe, and we have no idea what they are. It must explain what happened at the exact moment of the Big Bang. It must tell us what is inside black holes. And it must work at every scale from quarks to galaxy superclusters. If we ever find the theory of everything, it will be the greatest intellectual achievement in human history. One equation describing all of reality. The final word on how existence works. If this video expanded your mind even a little bit, do me a huge favor and smash that like button. And subscribe because we have so much more mind-blowing content coming your way. The theory of everything remains the ultimate mystery. And honestly, the fact that we are even smart enough to ask this question is pretty incredible. We're made of atoms, trying to understand atoms. Maybe we will solve it tomorrow. Maybe never. But the search itself has already taught us so much about reality. And that journey is far from over.